This lesson is going to be on systems and how we use systems to determine the various forces within the system. So today's objectives is we're going to define what a system is and how do we use this system to calculate acceleration and how does that help us calculate internal forces. At the end of this lecture, we're going to actually take a brief look at pulleys and how pulleys are kind of a variation on the system. Okay. First off, the definition of a system is a single object, or more specifically, a collection of objects and the forces between them. The objects must be connected in some way so that they all have the same acceleration. If they don't have the same acceleration, then I can't really treat them as a system, okay? The objects are going in different directions or moving independently of each other. If they're independent of each other, then it's not a system. Okay. Later on, we're also going to talk about what a closed or an isolated system is. Basically, a system with no unbalanced external forces. That's going to be used in some of the units that we're going to encounter later on. So, a system as a single object. We're quite used to treating objects as just a collection of smaller objects, okay, whether it's atoms or molecules or individual parts of a car. We treat it all as just one object because it moves as one object. Okay, so this is an example. Okay, I have a train. Each one of these cars in the train, the engine and the three cars, they all have a mass of m. And I can treat it as four separate objects, or I can also treat it as one large object. Okay, one train of mass 4m. Okay. And because I can treat it that way, I can ignore the internal forces. Okay, the forces between the engine and the first car and the second car, and the second car and the third car. Okay, the reason I can ignore them is because there's a Newton's third law pair in operation between these cars. Okay, so yes, the engine pulls the first car, and the first car pulls the second car pulls the third car. But just in the same way, Newton's third law says the third car pulls the second pulls the first pulls the engine. And because Newton says they're equal and opposite, they cancel each other out. So those forces are balanced. When I add a positive force and a negative force of the same magnitude, I just end up with 0. Okay, so those forces can be ignored, and I'm left with just one big train of mass 4m. And if I draw a free body diagram for it, I just end up with the up and down forces. I can mostly ignore those two because those forces are balanced, and the force of the engine on the train going forward. From there, I can apply Newton's second law that says my acceleration is going to be equal to my net force divided by that mass. In this case, the net force is just the force of the engine, and the mass is 4 capital M. Okay, so that's the system and how we can look at it as a system. Okay, we just take all the mass, make one big object with all of that mass. Okay, and that helps us because we can now find the acceleration of every single object in that system. Remember, they move as one object. Okay, so by doing so, a lot of times it's easier to calculate the acceleration of all the objects together. And that additional information will allow us to analyze some of those internal forces a little bit more easily. So here's an example. Okay, I have a 5 kilogram block tied to a 3 kilogram block. Okay, there's a string between them, and meanwhile the force is only pulling the 3 kilogram block. Okay, so the force pulls it at 20 newtons. Calculate the acceleration of the 5 kilogram block. Okay, since this is a system, they move as one object, I can treat it as such. Okay, the acceleration of the 5 kilogram block is the same as the acceleration of the 3 kilogram block, is the same as the acceleration of the system. So I'm going to treat it as a system. Here I take my 5 and 3 and combine it into one 8 kilogram block being pulled by that 20 Newton force. Okay, so my acceleration is simply going to be that 20 newtons divided by 8 kilograms, or 2.5 meters per second squared. And that's the acceleration of everything, the 5, the 3, and the combined 8. Okay. And the continuation problem now says, okay, I'm pulling the two blocks with a force of 20. What is the tension in the string connecting the two blocks? Okay. A common mistake people do is they say, well, I'm pulling with 20, therefore the 5 is being pulled with 20. But that would be incorrect. Okay. Sometimes people have it and say, well, half of it pulls the 3, half of it pulls the 5. No, that's not correct either. Okay. Instead, we have to look at it and say, well, the tension is an internal force. And I know the acceleration. I just figured that out. It was 2.5. So if I draw the free body diagram for the 5 kilogram or the free body diagram for the 3 kilogram block, okay, I end up with this, but I also know my acceleration is 2.5 meters per second squared to the right. Okay, so on both diagrams, I get that extra piece of information which I didn't have before. Okay, so applying that extra piece of information to the 5 kilogram block, okay, the free body diagram on the left, okay, I basically apply that 5 kilogram block. Net force is basically the force of the rope, and I'm basically left with the force of the rope being 12.5 newtons. Okay, and that's what having that extra acceleration gets me. Sometimes people ask, does it matter if I use the 3 kilogram block or the 5 kilogram block? No, the math still works out the same. The 3 kilogram block is just that one extra force, slightly more complicated, okay, because I have two horizontal forces on the 3 kilogram block. Okay, on the 3 kilogram block, I have the 20 Newton positive force and the negative force of the rope. The two forces of the rope, because it's the same rope, it's the same magnitude force. Okay, so plugging that number in, I get the same 12.5 for the force of the rope. Okay, so it really doesn't matter. One's a little bit easier than the other. That's the only difference. Okay, so if I use it as a double check, I'm good. Okay, I get the same number. If I don't treat it as a system, I'm forced to treat each object separately, just like we did on the free body diagram practice at the beginning of this unit. Okay, the last problem had those two blocks. You have to do two free body diagrams. Okay, yes, both objects have the same acceleration, so that's a variable that I'll have to solve for. The force of the rope is also the same because it's only one rope. Okay, but I would end up with these two equations. Okay, on the 5 kilogram block, it's the acceleration is equal to the net force of the rope, divided by 5. On the 3 kilogram block, acceleration is the positive 20 plus the negative force of the rope, divided by 3 kilograms. Okay, the force of the rope is basically the same, again, same rope, same force. So I'm left with basically two equations, the force of the rope and acceleration. Two equations, the left equation and the right equation, and two unknowns, the force of the rope and acceleration. I can solve this using a number of ways. In this case, I would just set the two accelerations equal to each other and solve, and again, I would end up with the force of the rope being 12.5. Okay, this is not incredibly complicated, okay? Yes, you have to go through a system of equations, which is slightly more complicated, but I only also have two objects here. If I have more than two objects, it starts to increase in complexity somewhat. So you do need to be, I still think having the systems approach does make things a little bit easier. So that brings us to the add-on, okay, pulleys. Okay, a pulley in a system changes the direction of the forces. It's still a system. The two objects still move kind of as one object. What I mean by changes the direction of the force, okay, the force on this system is basically just gravity on M2 pulling it down. Okay, so if that's pulling down, why does M1 move to the right? It moves to the right because the pulley changed the direction of the force. Okay, so we need to envision this as just a system. Okay, in this case, it's a system with just a mass of total mass, M1 plus M2, nothing's changed there. Okay, but in this case, the only force making this system move is the force of gravity, M2G. Okay, there aren't any other forces. Okay, the force of the rope, that's an internal force. We can ignore it. The force of the gravity on M1 is canceled out with the normal force of the surface on M1. Okay, so those forces don't matter. I'm left with just M2G pulling it one way. Okay, so in that case, the acceleration in this system is going to be the net force, or M2G, acting on M1 plus M2. Okay, so that's what you're going to need to do with a pulley. Okay, envision what are the two forces pulling. Okay, remember, one pulls one way, there may be a force pulling the other way. If there was friction on M1, that would pull the other way. Okay, and what is it acting on? The combined mass of both objects. Thank you.